All right, so one of the really nice things you might have noticed as we were working through some of those examples of this modulo 5 setting is that this idea of congruence classes seems to, in a sense, partition the integers. So what I mean by that is if you take this massive set of all of these possible integers, so in this case I have this fancy, handsome z in this case, and I've actually represented a good chunk of these integers, but I know that this set is going to be infinite, so at some point in time I don't want to keep on writing. I'm just going to do this little dot 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 to indicate that this list is going to keep on going in both directions in this case. I know that the integers don't stop at 5, and they most certainly don't stop at -5. They do continue on in both directions. So what's going to happen is that if you look at this massive collection of integers, I'm going to slowly start grabbing some of those things and throwing them into their correct bin. So the idea is that in this case, I'm going to look at all these numbers that are going to be multiples of 5. So in this case, it's going to be all of those numbers that are going to be congruent to 0 modulo 5. And if I take those things, I can throw them out of this list. In this case, I'm going to dump them all into this collection of all of those objects that are congruent to 0 mod 5. What I can do next is I can go ahead and grab all of those things that are going to be congruent to 1 mod 5. So if I grab the 1, if I grab the -4, if there was a 6 here, I'd grab that, and all of those are going to go in this congruence class of 1 modulo 5. Next up, you could look at all of those things that are going to be congruent to 2 mod 5. So the 2 is gone, the -3 is gone, the 7, if it was there, would be gone as well. Next, you could take all those things that are going to be congruent to 3 mod 5. So I'd have the 3 here, I have the -2, and you go from there. And last but not least, you're going to have this collection of all these things that are going to be congruent to 4 modulo 5. So in this case, I would have this 4. If there was the 9, it'd be gone, as well as that -1. And you very quickly see that you've used up all of these integers. That is, every single one of these things belong in one of those congruence classes. And we know these things are pairwise disjoint, so they're only going to exist in exactly one of these things. So the idea is that I can take this massive collection of all of these integers and I can partition these things into 5 really nice little sets. It's going to be the set of all those that are 0 mod 5, 1 mod 5, 2 mod 5, 3 mod 5, or 4 mod 5. Those sets are disjoint, so that is, they don't intersect at all, and I know that every single element is going to be in at least one of those. And we know in this case it's going to be only in one, exactly one. So what that's going to give way is going to be this notion of what are these integers modulo n. So in this case, if I look at this idea of what are the integers modulo 5, what I'm going to do is I'm going to form a new set. And so here's where a little bit of somewhat awkward notation is going to come into play. The way that we initially define these things is going to be very different than how we actually use these things in practice. But the idea is very simple. It's this idea that all of these numbers that behave like 4 modulo 5, we lump them into their own little set. And what's going to happen is that when we do arithmetic on these things, all I really care about is that 4. I really don't care about 9, and I don't care about -1 in this mod 5 setting, because all those things are going to behave just like the 4 does. So what I'm going to do in this case is I'm going to define these integers modulo n, which has a kind of weird notation. It's going to be this z with a subscript of n. So in our case of mod 5, it's going to be a z with a subscript of 5, and it's simply going to be a collection of those 5 congruence classes. So it's going to be this set of all those 0 mod 5, 1 mod 5, 2 mod 5, 3 mod 5, and 4 mod 5. So actually what this is, it is a set of sets. So it's kind of a really awkward thing to see. If you think about this in the array world, you're going to have an array of arrays. But really all I care about is that these individual things are going to be identified with their particular numbers. So it has really gross notational structure and things like that, but all I'm really going to use in this situation is that all of the elements that happen to be in this congruence class of 0 are all going to behave the same. So anytime I do work, I might as well just do work directly on 0, because those properties are going to hold for everything else in that congruence class. The same thing for 1, the same thing for 2, and 3, and 4. So in this case, we could actually continue pushing this idea. So the next example I have is this z sub 7. So all you're going to have in that situation is you're going to have 7 different congruence classes. So 1, 2, 3, 4, 5, all the way up to 6 in this case. And you can very quickly see that it's really obnoxious to constantly keep on writing these brackets over and over and over and over again. It's really cumbersome. It takes a lot of time to even type those things, even more when you try to handwrite these things. So often due to laziness is actually exactly what I said in this case, because it's most certainly why we do this, because writing those brackets out over and over and over again is time consuming. We often drop this bracket notation, and we're going to view this kind of integers modulo some number simply as this collection of numbers from 0 up to whatever number you're kind of stopping at. So in this case, it's always going to be 1 less than the number you're looking at. Because in this case, I know that if I'm looking at 0, 1, 2, 3, 4, 5, and 6, that 7 doesn't need to be counted for because 7 is congruent to 0 mod 7, so it doesn't make sense to even kind of think about that as being something else, because 7 is going to live in that congruence class of 0, so we've already accounted for it. So in this case, what we do end up seeing is that there are going to be some very nice numbers that we're going to want to do modular arithmetic on. One of those numbers happens to be the number 26, and the reason why we might be interested in the number 26 is because the English alphabet that we work with, at least kind of the lowercase or the uppercase version of this thing, happens to have exactly 26 characters. If you want to jump this up to a slightly larger set, including kind of capital and lowercase numbers, you'd have to double that 26. And if you wanted to include the entire ASCII alphabet, you'd have to go up to whatever, 128 or something like that as well. So you very quickly can change that little subscript to whatever kind of world you're trying to work with. A lot of the computation we're going to be doing in some of these examples of ciphers and things like that is going to be working in this mod 26 world, just kind of thinking about all of our messages are going to be capitalized, so we're shouting at you as we go. And it also just makes it a little bit easier to work with 26 than it does to constantly have to do all this arithmetic modulo 52 or something bigger than that. So what's going to happen in this world is that we do actually end up creating an arithmetic on these objects. What's going to happen is that we're going to have the ability to add and multiply these things together. And the nice thing about this is that the addition and multiplication works exactly like you'd expect to. What's going to happen is that if I wanted to, let's say, add the numbers, let's change away from this mac and cheese yellow. So let's say if I wanted to add the numbers 3 and 5, so it's all done in this kind of horrible, obnoxious notation world. What's going to happen is that if you're going to add these two congruence classes together, all you're simply going to do is you're going to take those elements 3 and 2, add them together, and that's exactly what's going to happen. So in this case, it's defined as taking 3 plus 2, and then doing that in that modulo 5 setting. So the addition of those two congruence classes is simply going to be the congruence class of 5 modulo 5, but we know that 5 actually reduces, so it's going to kick out a 0 mod 5. So it's kind of this weird arithmetic that we've dabbled into a little bit as we kind of were first starting to see this notion of congruence and things like that. We do know some really weird things can occur. So in this case, I'm taking two congruence classes that are not 0, but if I add them together, it kicks out the 0 congruence class. Likewise, if I take these objects, let's say 3, and I'm going to introduce this new multiplication, which is this circle with a dot on the inside of it. So if I take the congruence class of 3 and if I multiply it with the congruence class of 2, what that's defined as is going to be this multiplication of 3 with 2 in this modulo 5 setting, which is going to kick out, in this case, a 6 modulo 5, which actually nicely reduces down to a 1 mod 5 because that's how 6 is going to reduce. I know that these two congruence classes are equivalent, actually equal in this case, and it's always better just to talk about the thing that has that smaller number. It's the same reason why we didn't continue on this list going higher, because we want to stop, because once I have this kind of doubling up of things, it doesn't make sense to represent 7 because I already have the 7 in the 0. So in this case, that's exactly what's happening here. I went up to the 6, but then I know what 6 actually reduces to. It reduces back down to a 1, which puts me right back into this set z sub 5. So you can actually keep pushing that idea farther and farther, and you can actually create what are referred to as these gigantic addition and multiplication tables for these kind of modular arithmetic. So in this case, if I look at 3 and 2, I know how to add that. We added up the 3 and 2 together, creating a 5, and we reduced that 5 down to a 0. Well, if you create one of these kind of classic, elementary school addition and multiplication tables, what I'm going to do is I'm going to take all of the elements in z sub 5 up across the top, and I'm also going to double list them on the bottom part as well. So in this case, if I add 0 and 0 together, it does kick out a 0. A 0 and a 1 is going to kick out a 1. A 0 and a 2 is going to kick out a 2. Likewise, the 3 and the 4. I know that the 3 plus a 2, so the 3 and the 2, if I add those things together, it's going to kick out a 0. Likewise, if I do that in the opposite order, so if I take a 2 plus a 3, it's still going to kick out a 0. So you get this kind of nice computation that comes into play as well. So in this case, actually not a whole lot of reduction had to be done. The reduction is only going to happen in that bottom half of that table. If you take, let's say, 4 and add it to 3, well, we know that that's going to add up to whatever, 4, 5, 6, 7. And if I reduce a 7 modulo 5, it's going to kick out a 2. So that's why that object is existing down there. So you can do the exact same thing in the multiplication side of things, and there's actually a bunch of really nice things that are going to occur when I look at this in this multiplication setting. So in this case, I did the practice example of taking 3 and multiplying it by a 2. So here's the 3, there's the 2. If I multiply those things together, I do know that it reduces down to a 1. If I multiply it the other direction, so if I take the 2 first and multiply it by this 3, what's going to happen is, well, I'm still going to get a 1. So there's this nice commutative property. I don't care the order that I multiply these things in. The same thing is going to happen in the addition. I don't care if I take a plus b or b plus a. Those things are always going to kick out the exact same answer. which is really nice property to have. That's one of the fundamental things that I do want to not break. I want to have this notion that I don't care the order that I multiply or add. The parentheses and things like that are going to come up in their own kind of awkwardness, but for now I want that property to at least be satisfied. The other super important thing that's going to happen in this multiplication world is going to be this idea of what things are actually going to multiply to make a 1. Things that multiply to make a 1 are going to become a fundamental concept in this modular arithmetic. This is going to be this notion of a multiplicative inverse. And if you go back to thinking about trying to solve equations when you're back in middle school and things like that, if you had 3x equals something, you need to know this notion of how do you get rid of that 3. Well, classically in your algebra setting, you're just going to divide by 3 or multiply by 1/3, which is actually the notion of what is the multiplicative inverse of 3 in the classic algebra setting. In modular arithmetic world, I'm not going to have this notion of division. So just right off the bat, just start to ingrain that in your head, is I don't have any idea of what division means in this world. I know what addition is going to do and I know what multiplication is going to do. I don't know what division is going to do. So in this case, I'm going to have to think of other ways to get rid of objects, and that's exactly where this multiplicative inverse is going to come into play. So in this case, if I think about a 3 and a 2, well, if I multiply them together, it's going to kick out a 1, which is just as good as dividing, quote unquote, by a 3, because that's going to give me down to a stage that I can actually do some computation. So that's actually going to be what's going to happen as we move forward. The idea is that if I have a 3 multiplied by a congruence class of just x in this case, and let's say that's equal to a 2. Well, what's going to happen is that I'm going to want to start to think about how do I solve this expression for an x. So what's going to happen in this case is that I'm going to multiply both sides by a 2 on the left-hand side in this case, because I know that 2 times 3 is going to kick out a 1. We see that happening in this table a couple different places, so that's going to be the approach that we're going to take. So this idea of seeing all of these little 1s in this table is going to be a fantastic property, and it's actually going to be the property that's going to be shared anytime you do this reduction modulo a prime. If I don't have a prime in this place of that 5, some things are going to break down. It's going to become a little bit more awkward to work with. There's still going to be some computation we can do, but it's not going to be quite as nice. So actually in the next video, we're going to see this idea of trying to solve for things as we move into the world of affine ciphers. And all an affine cipher is going to be this idea that I can take some message, garble it up, and do a bunch of things to it, send it off to you, and you're going to receive some nice garbled mess. And you want to be able to actually take that garbled mess and recreate that message I tried to send you. So that's exactly where this idea of modular arithmetic is going to come into play. You can see this idea of multiplying things together is going to create weird numbers. The idea that 3 times 2 is going to kick out a 1 is weird from the computational side of things. It's going to be good on the encryption side, the idea that I'm going to take objects, muck them up, and create something else entirely. So that's what we're going to do in that next video, is see a little bit of these early ciphers. They're not very secure, but they do give us good practice on working with some of these congruence classes.